It doesn't matter.
I noticed your mom called you Mike. I have a son named Michael, and I'm always calling him Michael, and he always reminds me that he goes by Mike. So,
Yeah, I don't really care.
no, that's like me. I don't care if it's David or Dave. All right, what are we doing today?
Same stuff. We're just going to continue the chapter test.
All right.
Hold on, I'm getting to it. So, alright, so the equation is p of x equals 2x to the 4 minus 7x to the 3 plus x squared minus 18x plus 3. It says use the Socrates rules of signs to determine how many positive and how many negative real zeros p can have.
Wow. Okay. I don't know Socrates' rule of signs. So, and I don't think I have that in my book, because I have not heard of that. And I've been through this book 5 times. What else are you doing with polynomials like this? You must be using the rational factor theorem. You know what the rational factor theorem says? P over Q?
Yeah.
Says that if you have a higher degree polynomial, in other words, something bigger than a quadratic, usually we're working with cubics, if you have that, then and if there are rational zeros, then the numerator of the rational zero is a factor of the constant, and the denominator is a factor of the coefficient on the first term.
Yeah.
So if
I know the PRQs.
yeah, these are brutal because each of these problems takes about 20 minutes to solve. Who knew that it was so hard to solve quartics and cubics? You know, people think it's hard to solve a quadratic if you have to plug it into the quadratic formula. But there is no cubic formula, and there is no quartic formula. So the only way to solve for the zeros of these higher degree polynomials is with a lot of legwork, a lot of grunt work. In other words, if I was trying to find rational factors of this, first of all, the fact that it's a quartic tells me that it has at most 4 solutions. A cubic has 3, quadratic has 2, a linear has 1. So there's a law that says the number of solutions can't be any higher than the greatest power. So there might be 4 solutions to this thing, can be 4, but my numerator of a rational solution, if there's a solution like x equal 4 or x equal 5 or x equal 3 halves, that's a rational solution. And it would tell me that my numerator has to be either 1 or 3, plus or minus 1 or plus or minus 3. Those are my 2 possibilities. And my denominator has to be plus or minus 1 or plus or minus 2, the factors of the coefficient of the x to the 4th. So that tells me my possible rational factors are plus or minus 1, plus or minus 1/2, plus or minus 3, or plus or minus 3 halves. You see how I got all 4 of those from this?
Yeah.
Okay. So the next step, in other words, if this was a test problem and you gave me this function and said factor it, I would have to then start trying. I would use synthetic substitution or synthetic division, call it whatever you like, to try each of these 8 solutions until I found one that worked. Once I found one, I would divide it, reduce that thing to a to a cubic, go again. Same process over again. Finally, you get it down to a quadratic, and once you get it to a quadratic, you can always solve that by using the quadratic formula if you can't factor it easy. But anything bigger than a quadratic needs to be whittled down to its linear factors and a quadratic, or 4 linear factors, or 2 quadratics times one another perhaps. But the starting spot usually is this. However, the fact that you're telling me that Aristotle, Plato, Socrates, that Socrates has a rule that will tell you the number of positive and the number of negative solutions might be useful. Do you know what his rule is?
I don't. I'll look it up. I'll see.
Yeah, you should be able to go back in that chapter and see an example where they tell you how to apply his rule. That's probably much easier than this. Although that's not going to tell you the solution. That's just going to tell you how many positive and how many negatives there are. Now there are other rules like maximum value that X could be that you can use synthetic division to come up with, an upper bound or a lower bound, and that will help us rule some of these possible answers out. In other words, if I came up with an upper bound of +2, then I wouldn't have to try this +3 when I go to try each of these to see if they're a 0.
All right. Well, it says show that 4 is an upper bound and -1 is a lower bound.
Okay.
That's one of the parts of this question.
Okay, so 4 being an upper bound. Now, I thought that this might have something to do with upper and lower bounds. We're going to use synthetic division. Go ahead and do this synthetically for me. What goes here?
2, 8, 1, 4, -3.
Hold on. Where'd you get -3? 1 and 4 is 5.
Yeah.
Okay.
We're adding, I forgot. 5 times 4 is 20. 2, 8, for the remainder of...
Since each of these answers has a positive sign in front of it, it means 4 is an upper bound.
Okay.
If it's alternating, it's a lower bound. So he said prove that 4 is an upper bound. This proves it. Now let's prove, what was the other one?
-1.
So to prove that -1 is a lower bound, we need to produce an answer that alternates. Plus, minus, plus, minus, plus. And assume a 0 is whatever it needs to be, if you have a 0.
Okay.
Actually, I'm not sure about that. I would have to look one up. Does your example in the book have one with a 0 in the answer? I think you just ignore the 0, and you still have to alternate. In other words, if this came out to be 0 instead of 10, it would still be a lower bound. because
Yeah.
I still alternate. I go plus, minus, 0, minus, plus. So I'm still alternating if I have any zeros in my answers. But that is the way that we can tell that in other words, if I'm then going to use the rational factor theorem, I don't need to test minus 3. I don't need to test minus 3/2, because what Socrates' rule says is that minus 1 is a lower bound. I cannot have any answers that are less than minus 1. And I can't have any answers greater than 4. So I wouldn't have to try all 8 of those possibilities. I could rule out 2 or 3 of them. So that's the advantage in knowing your upper and lower bounds.
Mm-hmm.
Okay?
Draw a graph and use it to estimate the real zeros.
Of this function?
Yeah.
Okay. I'm going to do this on Wolfram. I presume when they say draw a graph, they mean on your calculator.
Yeah, we're allowed to use it there.
I mean, that's why I say I'm assuming that that's what they mean. Hold on.
Yeah.
So if I want to graph this, I'll just say, I can just put the function. I don't even need to say y equals on Wolfram Alpha. Are you familiar with Wolfram Alpha? It's a great little online calculator. It's really better it's better than your TI, and I'll show you why, because it'll tell us the zeros without doing a trace or any of that other garbage. Not only that, but it restates your function to make sure you typed it in right. Right there. Did I type it in right?
Yes. Oh, yeah.
Okay. So there's my function. It'll graph it. And it'll graph it in 2 different scales. So it looks like there's how many zeros?
2.
Which probably means there's 2 real zeros and there's 2 complex zeros.
What's the difference between real and complex?
Complex has imaginary numbers in it.
I'm so like confused. What is the whole imaginary numbers? Where are we getting these from?
Square root of -1 is equal to I.
Mm-hmm.
So if I am solving a quadratic formula, then I might have I might end up with something like 8 plus or minus the square root of 80 minus 96 all over 2. So let's say I plug in, I've got a quadratic, I plug it in, and I get this as an answer from the quadratic formula. Well, what is that? That's 8 plus or minus, this is -16. So the square root of -16, I'm going to write as the square root of -1 times the square root of 16. Okay, you with me?
Yeah.
Okay. That's a key step, breaking it into that, because now I can just replace that with I. So I have 8 plus or minus, this is the number 4, I all over 2. Well, now I'm going to divide each of these by 2. So I get 4 plus 2I would be my answer. This is the real part. This is the complex part. And
okay.
I know that doesn't explain to you why there is such a thing as an imaginary number. Think of it kind of like when they first invented math, they didn't have negative numbers. Nobody could understand why you needed negative numbers. Nothing in nature was negative. If you wanted your dimensions of your corral, there were no negative numbers. It was 0 or positive numbers. That was the only thing that existed. What happened was they realized that there is a huge mathematical benefit to having negative numbers. It's useful for solving all kinds of math equations. Same thing with imaginary numbers. Most of the time, if before you get to imaginary numbers, if I say, what's that? You'd say, that doesn't exist. That's outside the domain. You can only have positive numbers that you take square roots of. But once you learn about imaginary numbers, we know that's equal to I. So what's this equal to?
Root 4I.
Which is equal to?
2I.
So that's how you convert radicals of negative numbers to imaginary numbers.
Mm-hmm.
Okay?
So then complex and imaginary numbers are the same thing?
Yeah, the format
Okay.
is called A plus BI, and it usually looks like something like 2 plus 3I, or 2 minus 3I or something. Well,
Alright, now I understand that.
when you take a quadratic, we know that a quadratic has two solutions, but sometimes they're both imaginary. They may not have a real solution. If I take this quadratic, notice that there are no values of x that work,
Mm-hmm.
because this is always going to be positive. So how can you add 1 to a positive number and get 0? So if I try to solve this algebraically, I get x squared equal minus 1. Then I take the square root of both sides, so I get x equal plus or minus the square root of minus 1. So the solution is x equal plus or minus I. That's the only value of x that makes that equation work.
And so, technically nothing will ever fit in place of I, though.
Yes.
Is I like it kind of like its own number, I guess, in a way?
Yeah, you might say that. There's a very famous equation by Euler that says e to the I pi plus 1 equals 0. It's perhaps one of the most famous equations in math. And notice that these are the 5 most significant numbers in all of math. Pi,
Yeah.
e, I, 0, and 1. The fact that they would go together like that is astounding. It's just amazing when you think about it. Given that I is the square root of negative 1, given that pi is 3.14 whatever, given that e is 2.71, the fact that e to the I pi plus 1 equals 0, that was only discovered a couple hundred years ago by a man named Euler. So that's called Euler's formula. But back to our problem.
Yeah.
We know that there are 4 solutions to this, and imaginary solutions always come in pairs. In other words, if I told you that one solution to this would be 2 minus 3i,
2 plus 3I.
2 plus 3i is another solution. So there's 2 solutions. Between those 2 solutions, I can divide this polynomial by each of these, reducing it to a quadratic. Once I get
Will I run into problems where I have to do that? Have to
Yes.
divide by I?
Absolutely.
How would you do that?
Well, what they're going to do is they're going to say one solution to this is 2 minus I. Find the other 3 solutions. Well, I know that one more solution is 2 plus I. And now, if I take each of my solutions and divide it into the original polynomial, I get a reduced result. So I know there's 4 solutions, and if I look at that graph that Wolfram Alpha gave me, the only solutions that cross the x-axis are real solutions. Complex solutions don't have zeros on the x-axis. So remember that x squared plus 1? That plots like this. That's a parabola that's been shifted up by 1. Notice that it doesn't cross the x-axis. There is no solution to that. X squared plus 1 equals 0. There's solutions, but they're imaginary. Well, the same thing with this polynomial is there are not 4 real solutions to this thing. Otherwise, it would cross the x-axis 4 times. In answer to their question, estimate what the zeros are. Well, that 0 looks like at about 1/4, x equal 1/4. And this 0 looks like at about x equal 3 7/8. So that would be approximate solutions. We know that there has to be 2 other solutions because it's a quartic, so the other 2 solutions must be imaginary.
Alright.
The problems that you have to continually do in pre-calc is where they give you the polynomial and they give you one solution and you have to find all the others. So let's talk about if we knew what one of these solutions was, how would we divide by it? Let's see. I can tell you this.
Yeah, I can do those ones.
Okay.
You divide by the solution and then...
Notice that Wolfram alpha gives us our zeros right here. 0.1665 and 3.93. And here's my 2 complex solutions. It even gives us those. I don't want to go through this one because it's all these decimals. I'd rather go through one in its entirety. We have whole numbers because we can do it so much easier. But in other words, do you know how to divide this by x minus 2? Do you know how to do long division polynomial?
Yeah.
Let's just make sure you know how to do this. Step in doing this division. This is incidentally the same thing as synthetically dividing it by 2.
Yeah.
Okay. So what goes here?
2x cubed.
And then we take this and multiply it by both terms. And then we subtract. In long division, you're subtracting.
I mean, -7. Yeah.
See what I'm doing? I'm just all the way through. So that's how you divide. That's how you do long division with a polynomial divided by, let's say they told us that one of the solutions was x equal 2. Well, my first step would be to divide that 4th degree polynomial by x minus 2 to come up with the cubic. In other words, this times this would have to equal that. Then I would use whatever methods I could think of to try to find the zeros of that cubic. Once you get it down to a quadratic, in other words, once, say, another solution is minus 3. So I've got x plus 3 as one factor, x minus 2 is another factor. Divide both of those into that original polynomial, and I'll end up with a quadratic. The quadratic, I can then use the quadratic formula if I have to factor. So all of these kind of problems are just whittling it down one step at a time. Go from a quartic to a cubic to a quadratic. Okay, what other problems do you have that they want you to do here? Let's look at some of your problems, because I'm remembering all the problems that I've had various students have to do with this subject.
Alright, I think we're good with that one.
Okay.
Chapter 4 test.
Okay.
Sketch the graph of each function, say its domain, range, and asymptote, and show the x and y intercepts. So the first equation is f of x equals 2 to the power of negative x plus 4.
Okay. Let's rewrite that using a positive exponent.
1 over 2x. Yeah.
Uh-huh.
All right. Plus 1.
Okay. So they wanted the x and y intercepts and the asymptotes. Are there any vertical asymptotes? Is there any x? Is there any x that makes this denominator 0? That's what you're looking for a vertical asymptote.
Other than 0?
Vertical asymptotes are only caused by division by 0. In other words, if I look at this function, y equal 1 over x, well, that's going to have a vertical asymptote at x equals 0. So I'm going to draw the vertical asymptote. Also has a horizontal asymptote at y equals 0. Now to graph it, I graph it like that. So you only get vertical asymptotes when you're dividing by 0. Is there any way we can divide by 0 here?
Other than plugging 0 in for x, no.
No? Plugging in 0 for x, 2 to the 0th is 1.
Not enough.
2 to the billionth is a billion. 2 to the minus billionth is a positive number. So there's nothing that makes 2 to the x equals 0, which means there's no restrictions on 0. So for my domain, x, all reals. It's my range.
Does it involve the 4?
Well, it does, but range is a lot tougher to figure out than domain. Domain is rather simple. You just try to figure out what x can't be. If I have this function, well, x can't be negative. Not to confuse you with our previous talk on imaginary numbers, but x cannot be negative here.
Yes.
That's part of the domain restriction. If I say square root of that, well, x has to be greater than 1. Greater than or equal to 1. So we're always looking for domain questions. We're always looking as to what x can be and what it can't be. Range is much tougher. Range, well, let's examine this part of the function. As x goes up, what happens to 1 over 2 to the x?
It decreases.
Okay. So if x is infinity, this thing is equal to 4. Right?
Yeah.
Because eventually, as x goes to infinity, this thing goes to 1. That's where limits come in. You haven't had limits yet, but this thing would go to 0 is what I meant, not 1. So, in other words, this thing can never be 0, so can it be negative? Can 1 over 2 to the x ever be negative?
Yeah.
How?
I don't know.
Notice that a negative exponent does not mean a negative number.
Yeah.
If I have 2 to the minus x, well, let's let x equal 100. That's 1 over 2 to the 100th. That's a very small but positive number. Well, let's let x equal minus 100. Well, now I have 2 to the plus x. So that's 2 to the 100th power. So that's a very big number. So when x is big, this thing is small. When x is negative, this thing is big. So there's no way this thing ever becomes negative. And that's an important realization, because if this part can never be negative, then what is the smallest value that f of x can ever take on? 4.
4.
Now, I previously said this thing can never be 0 either, but as x goes to infinity, this thing goes to 0. This thing approaches 0, which means f of x approaches 4. So the lowest value in the range is going to be 4. Y has to be greater than 4. And it has to always be greater because this is always going to be some positive number. It's never going to be 0. So y cannot even be 4. Y has to be some number greater than 4. And we've already seen that if I make x minus 100, this thing becomes 2 to the 100th. So f of x can get infinitely large by making x a large negative number. So when you have problems like this, figuring out range is a little tricky. Let's graph that just so you can see. It is 2 raised to the minus x plus 4. Now, notice this graph never gets less than 4. It approaches it. As x goes to infinity, this thing will just keep getting lower and lower and lower, but it'll always stay above 4. So from this graph, I can read domain. Domain is negative infinity to positive infinity, right? I mean, I don't see any place on there where I can't make x. You always assume that these extend forever in that direction. But if I'm looking at range, I can see y has to be bigger than 4, always.
Yeah.
Let's see what else good stuff they give us here. They give us domain, all reals, y greater than 4. They give us the first derivative, they give us the integral, they give us the limit as x goes to infinity. This Wolfram alpha is the nuts, I'm telling you. All right. X and y intercepts. They wanted that on this. How do we get the y-intercept? The y-intercept's the easiest thing in the world to get.
Yes. Make x equal 0.
So what is f of 0?
5.
There's your y-intercept. How do I get my x-intercept? What is y? To get x-intercept, you need to set y equal to 0 and see if we can solve this.
1.
No. We've just decided we can't solve that. That has no solution. It's never equal to 0. It's always a number bigger than 4. So x-intercepts, none. So there's
yeah, we can see that from the graph.
Yeah, exactly. In other words, that, whoops, wrong graph. I must have it up here twice. No, I don't. Huh. Interesting. Okay. I'll leave it up there. But you're right. We could see from the graph that there was no x-intercept. It just keeps approaching the line y equal 4 and never goes below it.
All right, so these are two quick ones that I need help with.
Okay.
6 to the 2x equals 25. Write in logarithmic form. So is it just 2x equals log 25 to the 6?
No. Start with this. This is very important. Always. The logarithmic expression of this. Logs are what? There's one word that if you remember logs are, you'll never mess this up. Logs are exponents. So I know that that much has to be true. Now where does the b go and where does the y go?
B
B always goes there.
Yeah.
So the only other place for the y is there. So these two are equivalent expressions. Be able to go back and forth either way. So if I want to write this logarithmically, what I started out was y equals b to the 2x. So I'm going to say the log is equal to 2x because logarithms are exponents. 6 is my base. 25
Okay.
is my argument.
All right. So next one, write a equals 3 in exponential form.
That?
Yeah.
I'm thinking. Okay, so x must be 0. So I would say the log no, x can't be 0 because a to the 0 would be 1. I'm not sure what they're looking for here.
Well, that you just have to put it in exponential. Isn't that with like ln or e?
Oh, did you say e equals?
No, it says write the equation in capital A equals 3 in exponential form.
Capital A equals 3, and there is an exponential form of that. I don't get it, because that's not an exponential expression. That is a constant.
What if the A was an E?
Well, that wouldn't make sense, because E is equal to 2.71 ... It's like pi. It's an irrational number that goes on forever. So here, let me give you what I think they're looking for. 2.71 equals e to the 1 power. So if this is an exponential expression, so if I wanted to write this logarithmically, I would say the log of e, base e, of 2.71 equals 1. So if you gave me that, I can turn it into that.
Alright, they said the answer is e to the 3 equals A.
They had a equals 3. And they turned that into just e to the 3 equals a?
Yeah.
Something missing there, Mike. I'm not sure whether I'm missing something or they're missing something, but I don't.
Maybe they're missing the E.
I'm not sure what they're trying to do. Let's take a more common thing using e. Let's do e squared. Well, first of all, let's back up a moment. If I gave you this, that in logarithmic expression form.
Log of 2, 8 equals 3?
Uh-huh. In other words, it's the number on the far left raised to the power on the far right equals the number in the middle. It's the way I go the other direction. Okay? So, they're saying a equals 3.
Mm-hmm.
I still don't know where they're going with that. And I understand logs and exponential expressions very well, but I'm
lost. Like a typo.
I'm lost as to what they're trying to get you to see from that. If I wanted an exponential with e in it, let's see what e squared is. You have your calculator handy? Can you square e real quick? Approximately.
E squared 7.389.
Okay. So I can write that equation, right? So if I wanted to write this exponentially, logarithmically, I would say log base e of 7.38 equals 2. Well, log base e is the same as natural log. So now I'm saying this. Now go into your calculator and type natural log of 7.38 and see what you get.
1.998.
Right. In other words, 2.
Yeah.
Okay. So that's how the natural log works. It's just the log with a base that's not an integer. It's this odd number 2.71, which has a definition all to its own that involves limits, and we don't need to go over that right now. But there's a reason e is such a key number in life, right up there with pi.
So, next one, find the exact value of each expression.
Okay.
So one of them, 10 to the power of log 36.
Okay. If I take a number and raise it to an exponent that's a logarithmic function, and it has the same base, because you didn't give me a base, we're assuming the base of this is 10, this whole answer equals this part right there, 36. In other words, if I said 5 raised to the log base 5 of 22, that's equal to 22. In other words, as long as that is the same as that, then the whole thing is equal to that.
All right.
Okay? So that's one rule for logs that you need. What's another problem?
E to the power of 3.
To the power of 3?
Yeah.
Take that, do it in your calculator. It's the only way we're going to get an exact number.
Okay, so that one's straightforward.
Huh?
Log 3.
I mean, they said just give them an answer, right? They don't want the logarithmic expression of that or anything. If they did, I'd say y equal e cubed. That's this format here. So therefore, log base e of y equals 3, which is natural log of y equals 3. So if they want anything than an exact number, this would be the logarithmic expression of that.
Alright, this says find the solution of the equation.
Okay.
2 to the power of x minus 1 equals 10.
Like that?
Yeah.
Okay. In order to solve exponential equations, which is what this is, notice it's not an algebraic equation. We can't solve this algebraically. There is no way to take exponential equations and solve them algebraically. This is why they came up with logarithms, is to solve problems like this. Well, what can I do? I can take the log of both sides. Let's start with that. How about we take the natural log of both sides? Okay?
Yep.
Now there's a rule in logarithms that says if you take the log of a number to an exponent, I can take that exponent and bring it down in front. So this becomes the same as you with me?
Yeah.
Now it's simple algebra. Now we got an algebraic equation we can solve. X minus 1 equals natural log of 10, which is a number, divided by the natural log of 2, which is a number, which means x equals all of that plus
1. All right.
So whenever you have an equation that has the variable in the exponent, you almost always have to solve it by taking the log of both sides.
All right. So then,
Unless it's something like this. If it was, say, 4 to the x, now I can really solve this easier by writing 4 as 2 squared. Now combining that, so I get 2 to the x minus 1 equals 2 to the 2x. Now, because my bases are the same, my exponents have to equal one another. So x minus 1 equals 2x, and I can solve that. X equals minus 1/3. So unless it's a simple one where they're using the same exponential base, you can solve those without logarithms. But put a number in there that's not an exponential multiple of 2, like 3, and I got to use it. The only way to solve that is take the log of both sides. How about any log equations? You have any of those? Those can be challenging.
Log base 2 x plus 2 plus log base 2 x minus 1 equals 2.
Equals 2?
Yeah.
Okay. Remember our logarithmic rules? If you have the log of a plus the log of b, you got the log of a times b.
Yeah.
So how can I rewrite this?
X squared plus x minus 2.
So that's my first step in rewriting it. Now multiply those two together.
X squared plus x minus 2.
Now what can I say? Now I have a logarithmic equation that I can solve it if I can convert it back to exponential format. Express this exponentially for me. Remember, it's the number on the far left raised to the power of the number on the far right equals the argument. So 2 squared.
2 to the power of 2 equals.
And now you just have a simple quadratic. In other words, this becomes 4.
Do I still have to solve that, or?
Well, yeah. In other words, you're going to end up with this. And that factors nicely. X plus 3, x minus 2. So your solutions are x equals minus 3 and x equals plus 2. However, with logarithmic expressions, you got to be a little careful that you don't violate domains. We have to go all the way back to the original problem. What were my solutions? X equal minus 3 and x equal plus 2. Notice that one of those solutions has me taking the log of a negative number. Both of them do. In other words, this is not a solution because it violates the domain of the log function. The domain of the log function is whatever you're taking the log of has to be positive. It can't even be 0. I wouldn't even be able to have x be minus 2, let alone minus 3. But 2 works, because now I'm taking the log of 4 plus the log of 1. So whenever you're solving a logarithmic equation and you come up with 2 values, which you almost always do, just like a quadratic, always go back and check the domains, because almost always one of those is extraneous and has to be tossed out.
How did you get negative 3 and 2?
By factoring that final thing. In other words, we had the log base 2 of this quadratic equals 2. So then I said 2 squared equals the quadratic.
Okay.
Subtracted 4 from both sides, so I got 0 equals x squared plus x minus 6 equals x plus 3 times x minus 2. Gives me these two solutions. But this one is bogus because it violates the domain. So the only solution is x equal 2.
All right. That's all I really have for today.
Okay, well that's a lot. We covered a lot. Polynomials that are higher degree polynomials, logarithms.
I'm probably going to set up an appointment for Tuesday, too.
Okay.
So.
Sounds good.
All right. Thanks a lot.
I will talk to you probably Tuesday then. Thanks, Mike.
Yeah, see ya.
Bye-bye.